Right, so having spent one session on some basics of differential equations, let's try and understand some more formations. If you recall, I shared with you a first order differential equation of the kind m dx plus n dy equal to 0, where m and n were functions of x and y. M was a function of x and y, and n was a function of x and y. And I told you, you could write this as an exact differential. You could write, that means m dx plus n dy. This could have been, under certain circumstances, written as d of phi. This could have been written as d of phi. This equal to 0 would have given me phi equal to a constant, right? But will it always happen? No. This could be written as a perfect differential, d of phi, only if, that means an exact differential, if dou m dou y was equal to dou n dou x. If this happened, then this could have been written as d of phi, an exact differential, a perfect differential, right? What if it was not an exact differential? What if it was not an exact differential? For example, if you had like a x dy minus y dx, x dy minus y dx kind of a thing. Please open. Quickly, please settle down. X dy minus y dx equal to 0. Look at this. This cannot be written as, this cannot be expressed as d of something equal to 0, right? Because what is m? M is x, and dou x dou y, I'm sorry, x dy minus y dx. So this is my m. M is minus y, right? So dou y of m is minus 1. That is dou m dou y. That is dou m dou y. Dou n dou x, this is my n. So dou n dou x is plus 1. And very clearly, dou m dou y is not the same as dou n dou x, and it's not a perfect differential. It's not a perfect differential. However, if I did the following, I wrote x dy minus y dx. This, both sides I divide by x squared. Both sides I divide by x squared. Then what happens? Do you realize this is d of y by x? This is d of y by x. And it has been rendered a perfect differential. Which means, in its original form, with its original version, it was not an exact differential. But when I multiplied throughout by 1 by x squared, when I multiplied throughout by 1 by x squared, it rendered itself more available to being expressed as an exact differential. Yes or no? Right? So this 1 by x squared was really the key factor. It rescued you. It converted this into an exact differential. This 1 by x squared, when you multiplied the whole thing with 1 by x squared, it converted this into an exact differential. This 1 by x squared then, this 1 by x squared for this situation, this 1 by x squared was a key factor which converted this into an exact differential, and this 1 by x squared in this situation is what is commonly referred to as an integrating factor. Integrating factor. So essentially, this integrating factor would be different for different situations. In this situation, it worked out to be 1 by x squared. In some other situation, it could be something else, right? On very many occasions, this we can do by inspection. On very many occasions, finding integrating factor can be taken care of by inspection, But not always, Please come in. The integrating factor may not be readily available to you or obvious to you just by inspection alone. What I'm going to do is, in the next few minutes, I'm going to dedicate some time to sharing some common formations for which the integrating factor could be obtained with a set of rules, okay? So now, this time I'm talking of again a first order differential equation where m and n are functions of x and y, and it's not an exact differential. If it's not an exact differential, it means what? I'm talking of a situation where dou m dou y, differentiating m with respect to y, keeping x constant, is not equal to dou n dou x. Is not equal to dou n dou x. So it's not an exact differential. And if it's not an exact differential, we want to figure out integrating factors for such differential equations. We want to figure out an integrating factor for such differential equations where I multiply throughout by something and it renders itself available as a perfect differential. This is what I want to do, right? So let me take a situation like this first. Case 1. M and N are, say, homogeneous functions of the same degree. Have I discussed what homogeneous functions are? A collection of terms in which if the powers of x and y are added, they will be the same for every term. And the power to which they get added is the degree of the homogeneous expression, right? So this time I'm talking of m and n being homogeneous expressions, homogeneous functions, but of the same degree. For example, you know, m could be, say, x squared y plus y squared x. It's a homogeneous expression of degree 3. And say n could be x cube plus y cube. This is a homogeneous expression of degree 3. So I'm talking of m and n being homogeneous and of the same degree. So what works in homogeneous cases is y equal to vx. Y by x is v will always work. But if you have realized that it can make life really dirty, very cumbersome, taking y equal to vx led to very horrendous looking expressions and it was no fun dealing with them, right? Wish if there was something like this, if where m and n were homogeneous functions of the same degree, homogeneous expressions of the same degree, and I could just with out of inspection or out of doing something definite, I could obtain the integrating factors. And then I could collect terms suitably and write it as a perfect differential or an exact differential, right? Now, if m and n are homogeneous functions of the same degree, then the integrating factors for such a differential equation henceforth we'll write only if, integrating factor if, for such a formation is going to be 1 by mx plus ny, where mx plus ny is not 0. The integrating factor for such differential equations is going to be 1 by mx plus ny. 1 by mx plus ny. Provided mx plus ny is not 0. That means if I multiply throughout by 1 by mx plus ny, it will get converted into a perfect differential. Refer to the sheet we will have some example which will illustrate. So there is the first problem of the sheet. Look at the first problem of the sheet, 1a, which is like x squared y minus 2xy squared dx minus x cube minus 3x squared y dy equal to 0. Look at this. Look at this. So do you realize this is a homogeneous expression? And of degree 3. This is also a homogeneous expression and of degree 3. So y equal to vx will work here. Y equal to vx will work. But that's not what I want to deploy. I want to be a little, I want to do things more easily than doing y equal to vx here. Alright, that's why I'm taking recourse to obtaining the integrating factor for this. Right? Now, this I could have written as x squared y minus 2xy squared dx plus 3x squared y minus x cubed dy. Right? Yes or no? I absorb the minus sign here. So it's m dx plus n dy kind of a thing. So this then would be my m. This is going to be my m. A function of x and y. A homogeneous expression of degree 3. And this is going to be my n. Another homogeneous expression of degree 3. Right? So my integrating factor for such a situation is 1 by mx plus ny. So the integrating factor for this differential equation would be 1 by mx plus ny, right? Which is like 1 by this into x. That means x into x squared y minus 2xy squared. That is plus ny. N is this 3x squared y minus x cubed. Yes or no? This would be my integrating factor. This would be my integrating factor. And do you realize x cube y and x cube y will get cancelled here? And what this essentially gives us is 3x square y square minus 2x square y square, which is x squared y squared. That's my integrating factor. That's my integrating factor for this. Now let's see what happens when I multiply the whole thing with 1 by x square y square. Let's see what transpires in this differential equation. Alright, so I'm going to take to this differential equation and divide by x square y squared. So x squared y minus 2xy squared by x squared y squared, which is my integrating factor. Dx, please sit down, plus 3x squared y, yeah, please come in, plus 3x squared y minus x cubed by x squared y squared dy equal to 0. Let's see. I'm expecting this to be an exact differential. I'm expecting this to be an exact differential. See what happens. Can I remove the clutter from here? So let me carry out a division here. Let me carry out a division here. So this is like 1 by y minus 2 by x, isn't it? Dx plus this is like 3 by y minus 1 by minus x by y squared dy equal to 0. Right? Yes or no? Now, as far as 2 by x dx is concerned, not an issue. This is 2 log x. 2 d of log x. 2 d of log x. 3 by y dy is concerned, not an issue. This would be 3 d of log y. Right? So this is all right. This is all right. These are trouble-free terms. Right? Now, Let me look at the other two terms. 1 by y dx, 1 by y dx minus x by y squared dy, right? And this minus 2 by x dx, which anyways is not a problematic term, and 3 by y dy equal to 0, right? Now, do you see this is 1 by y dx minus plus x minus 1 by y squared dy is d of 1 by y, isn't it? It's d of 1 by y. It's d of 1 by y. And this is minus twice d of log x, isn't it? Plus 3 d of log y equal to 0. How about it? Derivative of first function into second function plus derivative of second function into first function, derivative of the product of functions. So these two terms club together to produce d of x by y. X is one function and 1 by y is another function, plus d of, this 2 can get inside this, so d of log of 1 by x squared, right? I'm using up the minus sign also, minus 2, so d of 1 by x squared plus d of log y cubed equal to 0. Perfect differential now, isn't it? This is d of x by y plus log of, if I combine these two, log of 1 by x squared plus log of y cubed equal to 0. Yes or no? Perfect differential. Do you see that? Perfect differential. That means this must be constant. This must be constant. And if I combine these two, it's going to be log of y cubed by x squared. So then, performing the last bit on this, x by y plus log of y cubed by x squared, that must be constant. Obviously, you expected one arbitrary constant. Why? Because if it was a differential equation of order 1. If it was a differential equation of order 1. Right? Works good for us, isn't it? That's the solution to this differential equation. Now, henceforth, if you encounter a homogeneous equation in x and y, for school consumption, if you want to take y equal to vx, I don't care, because that's what they'll understand. But for the sake of my class and for the sake of more serious exams, you encounter a homogeneous, you look upon that as mdx plus ndy equal to 0, and then multiply throughout with 1 by mx plus ny, which will turn out to be your integrating factor, and it will convert that into an exact differential. Convert that into an exact differential. That's how it works. It'll be pretty clutter-free and less cumbersome. Right? Yes or no? Now, so I said mx plus ny should not be 0. What if mx plus ny turns out to be 0? What if mx plus ny turns out to be 0 in a differential equation? Now that makes life really easy, because that's a more trivial case. Can I wipe this off? So if I have a differential equation in which 1 by mx plus ny happens to vanish, say I have a differential equation mdx plus ndy equal to 0, and if mx plus ny vanishes, now that's really a very easy case, because realize that this would give me m by n equal to minus y by x, and m by n from this is also minus dy dx. Yes or no? Right? And this would give me like a y dx minus x dy equal to 0. Divide by y squared. Derivative of numerator into denominator minus derivative of denominator. Denominator into numerator by denominator squared. You get d of x by y equal to 0. or x by y will be a constant. X would be c into y. So if mx plus ny turns out to be 0, now that's really a trivial case. You don't have to break your heads for such a differential equation, right? But when not 0 and you find m and n to be homogeneous functions of x and y of the same degree, then your integrating factor is going to be 1 by mx plus ny. It'll get converted into an exact differential. Clear? Now, can I wipe this off? All good, huh? Yeah. Yeah. Say, the second kind of differential equation you're going to encounter is y into some function of xy, function of x into y, function of xy, dx plus x, some function of xy, dy equal to 0. Something like this. This is yet another very commonly occurring form, where this then becomes my m, this is my m, and this is my n. This is my n. So I have like a m dx plus n dy equal to 0, where this is m and this is n. This will be an inexact differential. To convert this into an exact differential, the integrating factor is going to be for this. The integrating factor for such a differential equation is going to be 1 by mx minus ny, provided mx minus ny is not 0. And if mx minus ny turns out to be 0, then it's a very trivial case. Like I dealt with the earlier case, right? So we'll look at the case where mx minus ny is not 0. Then the integrating factor for such a differential equation would be 1 by mx minus ny. Let's see how to handle a situation of this kind. Get back to the sheet. Let's identify a problem which falls in this category. Okay. Look at one part C. One part C is y into xy plus 2x squared y squared dx plus x into xy minus x squared y squared dy equal to 0. See if it is of the same formation. See, this is my m and this is my n. This is m and this is n. And do you realize it's y into some function of xy? Isn't it a function of xy? Right? Plus x into, this is also a function of xy? Exactly this form. And it's, trust me, it's not an exact differential. You own responsibility to convert this into an exact differential, either by inspection or by what I have said. Right? So under the pressure of an examination, the inspection may not work. You know, if in a typical exam like environment, inspection may not always work until and unless you've had loads of practice. Then these integrating factors really come as your saviors. So let me obtain 1 by mx minus ny, the integrating factor for this differential equation, and see what transpires. Right? So the integrating factor for this is going to be 1 by mx. That means this into x, right? This is my m, so this into x. So this is xy into xy plus 2x squared y squared mx minus, this is my n, this into y, right? This is my n. So minus xy into xy minus x squared y squared. Yes or no? That's the integrating factor for this. Let's see what happens here. Hey, x square y squared and x square y square will cancel off from here. And there is 2x cube y cube plus x cube y cube. So 1 by 3 x cube y cube, right? See, for your board exams, you are allowed to multiply and divide a differential equation by something, but not use the word integrating factors. So what you do is, obtain this on the margin. They will not ask you how you obtained that. You could have obtained anything out of inspection. That cannot be put to doubt, right? So obtain this. If they don't allow using integrating factors and 1 by mx minus ny, classifying it as out of syllabus, then all right. So this you obtained by inspection, 1 by 3 x cube y cube. Let's see what happens when I divide throughout by 1 by 3 x cube y cube, and does it actually get converted into an exact differential or not, right? Let's check on that. So I divide by x cube y cubed. 1 by x cube, 3 times this, and 3 times x cubed y cubed, right? Let's see what happens. So 1xy will cancel this and will cancel this, right? So I'm doing like a x square y squared. This will become 1 and this will become 2xy. Yes or no? I've used one of the xy's to cancel an xy in the numerator, right? Now the other xy. Again, I use one of the xy's here. So this is like my 1 minus xy. 1 minus xy. Yes or no? As simple as this, right? And let's then start to manipulate. Manipulation means just ordinary collection of terms. So in any case, this by this is like 1 by 3 x squared y, isn't it? This by this, 1 by 3 x squared y plus, or I can just cancel the y here, I carry the headache. So 1 by 3 x squared y dx, right? 1 by 3 x squared y dx plus, when I divide this will be 2 by 3 x, 2 by 3x. Yes or no? Right? 2 by 3x dx plus, now again cancel this x with this x, right? And see what happens. 1 by 3x y squared dy, 1 by minus dy by 3y, right? That's equal to 0. Yes or no? Now, this is a no problem term because this will be 1/3 d of log y, a no problem term. This also is a no hassle term, 2/3 d of log x, right? Which means the remaining two terms would connive to create an exact differential. This is what you expect, and this will happen, guaranteed that will happen. See how it happens. Now, do you realize if I put these two together, then this is like 1 by x d of minus 1 by y, right? Yes or no? And if I take this, then, or what I could do is, I could take say 3xy common from these two terms, 1 by 3xy common, it's the same thing. These two terms, I take 1 by 3xy common, and then I'm left with 1 by x dx plus 1 by y dy. Yes or no? right? Right? This would be 2/3 d of log x, 2/3 d of log x, right? 1 by x dx. So this will be 2/3 d of log x. This will be minus 1/3 d of log y equal to 0. What is this? Dx by x, d of log x, d of log y, yes or no? This is d of log x, this is d of log y. So this is d of log x plus log y, which is d of log xy. This is d of log xy. Yes or no? So 1 by 3 xy, this would be d of log x plus d of log y, d of log xy. Xy plus 2/3 d log x minus 1/3 d log y. Yes or no? Please, Partho, please. Eat, drink and be merry, but don't disturb. God. Yes or no? Do you all understand everything that I have done here? Do you realize this is 1 by xy d log xy? Is it a perfect differential? This is log t 1 by t. What do you do? 1 by t d of log t. 1 by t d of log t. Huh? What would this be? Right? What would this be? 1 by t d of log t. So it's like you can take 1 by t and with a minus sign, right? Yes or no? And this is like something like L d of log L. What would this be? What would this exact differential be? Huh? Hmm? Hmm? DL? DL. It's going to be DL, isn't it? D of log L is 1 by L DL, isn't it? This is D of log L is 1 by L DL. So what is that going to be? Simply DL, isn't it? Where L is what? 1 by T. L is 1 by T, isn't it? Yes or no? Or right here you could have said this is 1 by xy d of xy. See, I could have said this 1 by xy d of xy. I could have said this, isn't it? See, I had like a 1 by xy d of log xy, isn't it? 1 by xy d of log xy. D of log of this is what? 1 by xy. This is 1 by xy d of xy, isn't it? Isn't it? And there is a 3 here. There is a 3 sitting here. So this is like 1 by 3 xy squared d of xy. dt by t squared is d of minus 1 by t. dt by t squared is d of minus 1 by t. So this is minus 1 by t. This is d of 1 by xy, isn't it? Yes or no? So this is minus 1/3 d of 1 by xy. Huh? Perfect differential? Yes or no? I hope you realize this. dt by t squared is d of minus 1 by t. Is d of minus 1 by t. 1 by xy. Right? So all's done here. This is minus 1/3 d of 1 by xy plus 2/3 d of log x minus 1/3 d of log y equal to 0. Done. Integrate both sides. When you integrate both sides, what do you get? Minus 1/3 into 1 by xy plus 2/3 log x minus 1/3 log y equal to constant. When you integrate both sides, this is what you get. Yes or no? Sounds all right? Some more versions on integrating factors. Some more versions on integrating factors. So case 3, I have m a function of x and y and n a function of x and y. This is my differential equation of first order and not an exact differential. Like if it's not an exact differential, what does it mean? Dou m dou y is not equal to dou n dou x. This is what it means. This is what it means. I now want to find an integrating factor for this. There are two more pertinent cases which I want to deal with. Two more pertinent cases that I want to deal with. Case 1. Let me call it A. Let me call it A. Obtain dou m dou y minus dou n dou x. Obtain dou m dou y minus dou n dou x. This is no longer 0. This is no longer 0 because if it were to be 0, it would be an exact differential. So dou m dou y minus dou n dou x, and you divide it by n. You divide it by n. Dou m dou y minus dou n dou x, and you divide it by n. And if you find that this expression is either some function of x, is not dependent on y, if this ratio is not dependent on y, it could be fx, where this fx could be a function of x, or it could also be a constant. This fx could also be a constant, right? This could be function of x or constant. The important thing is, it should be independent of y. It should be independent of y. If this turns out to be independent of y, if this is essentially independent of y, then you can call it fx. Then you can call it fx. Even though it could just be a constant, you would still call it fx. If this turns out to be independent of y and some function x, which could also be a constant, right? Then the integrating factor for this, is going to be e power integral fx dx. Then is going to be e power fx dx. Integral fx dx is going to be the integrating factor for this differential equation. If this happens, that means if dou m dou y minus dou n dou x by n, if it's independent of y, then e power integral fx dx is going to be the integrating factor for this, right? Case B. If dou n dou x minus dou m dou y by m, if this is independent of x, of x. That means it's a function of y alone. It's a function of y alone. Say it is f of y. Say it is f of y. Then the integrating factor for such a differential equation is going to be e power integral fy dy. That's going to be the integrating factor for this. E power integral fy dy. If dou m dou y minus dou n dou x by n is a function of x alone, then e power integral fx dx is going to be the integrating factor for this differential equation. If dou n dou x minus dou m dou y by m is independent of x, that means it's a function of y alone, call it fy, then the integrating factor is going to be e to power integral fy dy. It'll take a little while to get used to this, but it's not difficult at all. Let me illustrate this, and that would set matters right. Can I wipe this off? Look at 1 part D. X squared plus y squared plus 2x dx plus 2y dy equal to 0. First, ensure that it's not an exact differential, right? So, what's dou m dou y? This is my m. Differentiate this with respect to y. What do you get? Keeping x constant, you get 2y, right? Dou n dou x, 0. Differentiating 2y with respect to x, that's going to give me 0. Right? Now do you realize that dou m dou y minus dou n dou x divided by m divided by n which is 2y divided by n which is 2y. See, dou m dou x, dou m dou y minus dou n dou x is what? Is 2y, and divide that by n. N is 2y. Do you realize it's independent of y? It's independent of y? It's independent of y? And if it is independent of y, then my integrating factor is going to be e power integral fx dx. Fx is 1 in this case. Fx dx, dude. Dx. Fx dx. Right. No, you can't use fy dy. Then I have to divide by m. Right? So it's independent of y. So the integrating factor is going to be e power integral fx dx. That means e power x. E power x is going to be my integrating factor. Right, Vidu? So let's see what transpires on multiplying throughout with e power x. Do you understand what I've done here? Pakka na? Clear? So I looked at this difference and I just was checking whether this difference by this is independent of y, or this difference by n is this difference by this is independent of y, or this difference by this is independent of x. These are the only two things that you need to check. Right? And by inspection I can see that this difference divided by this will be independent of y. So integral will be e power integral fx dx kind of a thing. Yes or no? Good. So e power x then turns out to be an integrating factor for this differential equation. Right? E power x, that means if you multiply throughout with e power x, it would help. Right? Let's see what happens. Can I remove the clutter and work through the differential equation now? So let me multiply it throughout with e power x. Now again, this is an alright kind of a term. This is d of x squared. It's not bothering us, right? So in any case, I take this e power x into x squared dx plus e power x into 2x dx. That means this and this I combine. You'll see why. Because e power x dx is d of e power x into x squared, and 2x dx is d of x squared. It'll get into a product formation, right? So these two consumed. Now let me look at the other two. So this is like e power x y squared dx. See, e power x y squared dx plus, and there was a dy here. There was a dy here plus 2y e power x dy equal to 0. Right? Right. So see what happens. You get x squared e power x dx is d of e power x plus e power x 2x dx is what? D of x squared. D of x squared. Now look at this. This is y squared. E power x dx is d of e power x plus e power x 2y dy is d of y squared equal to 0. So this then is like these two together is what? D of x squared e power x. These two together is what? D of y squared e power x equal to 0, which is like d of e power x into x squared plus y squared, isn't it? D of this plus this equal to 0, or we must have e power x into x squared plus y squared equal to a constant. That's the solution to this differential equation. That's the solution to this differential equation. Yes or no? So it works, but trust me, when you become more accomplished with attributes of differential equation, some of these things which are obtaining out of results could also have been obtained by inspection alone, because you can jump through steps and see what's happening. You will have a superior x-ray vision into the problem, and you'll be able to mentally evaluate what to multiply and divide with so as to convert into a perfect differential. But until the time you reach that state, the results that I'm suggesting to you will come in very handy. Okay, let me illustrate one more from this. Can I wipe this off? Please sit down. One moment, please. Another differential equation. Let's be sure that it's not an exact differential first, right? Let's be sure that it's not an exact differential. What's my m? M is clearly 3x squared y to power 4 plus 2xy, right? What is n? N is 2x cubed y cubed minus x squared. That's n. So m dx plus n dy. What's dou m dou y? Differentiate this with respect to m, keeping x constant. So that's going to be 12 x squared y cubed plus 2x. Yes or no? What is dou n dou y? dou n dou x, beg your pardon, dou n dou x. That's going to be 6x squared y cubed minus 2x. Obviously the two are not equal. Two are not equal. Now if I subtract, say, dou n dou x minus dou m dou y. Dou n dou x minus dou m dou y. Let's say if I do this. I mean, it does not matter. See, you can mentally do that calculations. Dou n dou x minus dou m dou y. What does that turn out to be? Minus 4x minus 6x squared y cubed. Yes or no? Minus 4x minus 6x squared y cubed. Which is like minus 2 into 2x plus 3x squared y cubed. Yes or no? Do you realize what I did here? I took minus 2 common, x plus 3x squared y cubed. There are only two things that you have to check. Either divide by m or divide by n. Right? So if I divide by m here, m is what? This. If I divide by m, that is this. What happens? It will be a function of y alone. See, it's going to be a function of y alone. Do this. If I divide this minus 2 into 2x plus 3x squared y cubed, that means this. I want to divide by m. I want to divide by m. By m. What's my m? M is this. M is this. M is this. I take y common. See, reason I'm doing is because I see a 2 and 3, so I'm tempted to divide by m instead of n. Right? Because I see a 2 and a 3 here. That means I divide by twice xy plus 3x squared y to power 4. Yes or no? Divide by m, this is what I have. What happens? Right? So see, if I took y common from this, oh, there isn't a 2 here. This 2 is not there, sorry. This 2 is not there. So if I carry out this division, then this will be 1 by y. Do you see that? This is 1 by y. Minus 2 by y, therefore. Minus 2 by y. Isn't it? Multiply this by y, you get this. So this is minus 2 by y. Right? Which is independent of x. Good for us. Which is my fy. Oh, sorry. This 2xy. Yeah. Got me kya? So this is minus 2 by y. So my integrating factor would be what? My integrating factor would be e power minus integral 2 by y dy. Fy dy. E power fy dy. That's going to be my integrating factor. Got me? This is log of 1 by y squared. This is log of 1 by y squared. So this will become 1 by y squared. That's my integrating factor. 1 by y squared is my integrating factor. Yes or no? Huh? So let's divide by y squared throughout and see what happens to this differential equation. Let's see what happens to this differential equation on multiplying by 1 by y squared. Clear? One by y squared y squared, right? It should now convert into an exact differential. You expect that to happen, right? It should convert into an exact differential. So let me divide. So first of all, you know, this y will make this y cubed. Will do this, right? Now when I divide, I get like a 3x squared y squared dx, right? 3x squared y squared dx plus 2x by y dx plus 2x cubed y dy minus x squared by y squared dy equal to 0. Yes or no? What would you combine together? This is d of x cubed, isn't it? 3x squared dx is d of x cubed. So this is y squared, 3x squared dx is d of x cubed. Look at this. This is x cubed, 2y dy is d of y squared. X cubed, 2y dy is d of y squared. So plus x cubed, 2y dy I write as d of y squared, right? And then these two terms should be put together. These two terms should be put together. What can I do with these two terms? This is d of x squared, very clearly. Right. So this is 1 by y. This is d of x squared. And minus 1 by y squared dy is d of 1 by y. Equal to 0. Right now? These two in a product form, d of x cubed y squared plus d of x squared into 1 by y, right, equal to 0, or d of x cubed y squared plus x squared by y equal to 0, or x squared x cubed y squared plus x squared by y equal to a constant. That's the solution to this differential equation. That's the solution to this differential equation. Got me?